now is the time for us to look more deeply, more closely at how hexadecimal system works. We saw that hexadecimal numbers are a quick and easy way to represent 4-bit number between 0 and 15. And this system represents each number with a single digit. From 0 to 9 digits are the usual decimal digit, 0, 1, 2, 3, and so on. And from 9 on, we use the letter A for 10, B for 11, C for 12, D, E, and F till 15. So a group of 4 bits is called a nibble in computer science and digital electronics. And now we want to see what happens when we use a number composed by 8 bits. So 2 nibbles or a byte. And let's see all this using the 4-bit adder we built in the previous video. And the idea is to put together 2 4-bit adder and make one 8-bit adder. So using 2 circuits like this one and build one circuit capable to sum up numbers composed by 8-bit. So first of all, we want to transform this circuit in a sub-circuit, and to do it, the third thing we have to do is to erase all the output device contained in this circuit. So we have to erase all the hexadecimal display and the wires also. And the reason is that when we want to use a circuit like as a sub-circuit, we don't need to have any display closed inside the circuit, because if I want to take this circuit as a box, as a sub-circuit, a component, we don't need any display inside. If we want to have a display, we'll wire it to the circuit outside the box. I show you it in a moment. And another little change I have to introduce to the circuit is to erase this constant here. I remember you that we use a constant because the constant is a fixed value that doesn't change when you close Logisim and rerun the Logisim and reopen the circuit. But now I want to substitute this constant with a normal input bit, and I call this input bit carry in. And this overflow, it's better renamed carry out. In a moment you'll see the reason for this change. So now I have a sub-circuit named adder 4 bits, and I can open a new circuit adder 8 bits. And in this circuit I drag 2 4 bits adder, and now here you have carry out from the first adder and carry in into the second, and so we have to connect this one to this one. But as usual, it's better to move the sum, the result, so the sum in this position, and to move the 2 number A, B in the upper position. So before building the circuit, I go back to our adder and I move, this is the carry, sorry, This is the sum. I move it here. This is carry in, okay, is here. This is B, and this is A, and this is carry out. So, and as usual, I reshape, move the upper side of this box and this one, so the output pin and the input pin are inside the borders of the box. So now I go back to our circuit, and again I put in it 4 other bits, and now I connect the carry out with the carry in. And here and here and here and here we put our 4-digit, 2 group of 4 digits. Here you can see the circuit, the finished circuit, and take a close look at these two splitters. And for example, this one, this is a splitter with bit within 8 bits, so it splits a group of 8 bits in 2 subgroups, and you see the first subgroup is from bit 0 to bit 3, and the second one is to bit 4, from bit 4 to bit 7. So the purpose of this splitter is to split an 8-bit input into 2 groups of 2 nibbles to 4 bits output, and the same for this one here. And the splitter I used here in the output as the purpose to group together the output, the sum produced from this adder and the sum produced from this one, so 4 bits and 4 bits into a group of 8 bits. And here we put a 0 constant as input to the first 4 bits adder, and the carry out from the first 4-bit adder goes into the second 4-bit adders, and here is the carry out of the second adder, which we usually use as an overflow signal. So the circuit is not too complicated. I write the first number here, the second number here, and here you have the sum between these 2 numbers. The difference between this circuit and the previous one is that now I can sum together number of 8 bits. And I want to explain you better how it works using some hexadecimal display here. What about hexadecimal system? Hexadecimal system is a system of numeration which is an easy way to write down long binary numbers. For example, here we have quite a long sequence of bits, 8 bits, and it is difficult for us human beings to remember or to tell simply this sequence of bit 1 0 0 0 0 0 0 0 1. It's easier to split this 8 bits in 2 nibble, in 2 group of 4 bits. So these 4, the least significant ones, and these 4, the most significant ones. We ideally split this byte into 2 nibbles and represent each nibble, each group of 4 bits with just 1 hexadecimal digit. So for example, this 001 is 1 and this 100, the most significant nibble, is 8. In this case, we split this group of 8 bits in 2, and the lower one is 0011, which is 3, and the upper one is 0100, which is 4. So 4-3 in hexadecimal is a quick way to write, to represent this group of 8 bits. In the same way, we have this result, which we can represent in a better way in this notation. We imagine to split it into 2 nibbles. The lower nibbles is 4, and the higher nibbles is 1100, which is 12 in decimal system, which is C in hexadecimal system. So we write this byte, a byte is a group of 8 bits, we write this byte as C4. In this way, we can use hexadecimal number simply as a quick way to write down long binary number. For example, we can have even a 12-bit or 20 bits binary number, and simple, if we have a 20 bits binary number, we can write it down as 5 hexadecimal digits, and each digit represent, as always, 4 bits. So I think for now that's all we need to know about hexadecimal number and how we use it in digital circuits.